Hi class, welcome to your video on the continuation of applications of integration. This week we want to move into section 6.3 in our textbook and talk about volumes of cylindrical cells. So in this section what we're going to do is we're going to learn how to apply this new method. Alright, it's called the method of cylindrical shells to find the volume of a solid. Now the interesting thing is that this method is a lot like the previous sections that we've done. So last time we talked about finding the volumes of a solid revolution using the disk method and something called the washer method. Now this method of cylindrical shells will find the same exact volumes that we were doing before, just with a different take on it or a different way. Okay, so some of the problems that we saw or that you might have talked about or learned in the previous sections are very difficult to handle with the methods of the washer or disk. So let me show you an example. All right, so this one here would be really hard to do with the previous methods. All right, so let's consider this problem, and we're going to do it. This will be our first major example. We'll follow it through with the lecture. So let's consider the problem of finding the volume of a solid obtained by rotating around. Now this is important. The y-axis, okay, the region bounded by this. Y is equal to 2x squared minus x cubed, and y is equal to 0. All right, so this is the shape here. And like if we're going to go around the y-axis, right, this is important. If we're going to go around the y-axis, previously what we would have learned to do was this was a dy problem. You would have integrated with respect to the y variable. All right, so you would have had to take the outer radius, which I'm going to denote as x sub r here, and the inner radius and subtract them. But like, what's the equation for the outer radius? What's the equation for the inner radius? It's like really hard. All right, so if we slice perpendicular to get a washer, all right, the inner radius and the outer radius, we'd have to solve this equation in terms of y. And it's like, how would you, solve for x in terms of y? It's like, how would you do that? You know, like, you can't do it. Like, I can't just get from this, I just can't get x by itself. So using that washer method is not easy. So we're going to need a new method. All right, now notice here what we're doing with the washer method is if we wanted to go around the y-axis, it would be a perpendicular rectangle. So the idea here with this is like, okay, maybe instead of using a perpendicular rectangle, all right, to go around the y-axis, what if we used a parallel rectangle? So it was vertical, or it was vertical instead of horizontal. All right, so fortunately, all right, there is a method. It's called the method of cylindrical cells that is much easier to use in this case. So what I want to do in the first part of the video here is walk you through the setup. Okay, so going back to this problem, instead of using a perpendicular rectangle, what if we used a parallel rectangle? All right, so it's going to be weird. In the previous section, when you were integrating or revolving, around the y-axis, it was a dy problem. But actually, this time when I revolve around the y-axis, it's going to be a dx integral. All right, you'll see. All right, so let me walk us through this. So the figure below shows this cylindrical shell. All right, so it's a cylinder, and I have two radiuses. I have R1, which is the inner radius here, and R2, which is the outer radius. So like if you think back to here, what I'm going to do is I'm going to have like a perpendicular rectangle, and I'm going to have an outer radius and an inner radius, okay? All right, we're going to call the difference between the two delta R, and we have the height of the rectangle. You're going to notice this R here, and this is going to come into play. R is going to represent the average radius, so it's like the radius that falls between the two. All right, so we have delta R, the distance, height, and the average radius. All right, so the volume of this cylindrical shell, if you think about it, is calculated by subtracting the volume of the inner shell from the volume of the outer shell. Like I'm taking away this like shell in the middle. So to take it away in mathematics, you subtract it. So let's go through the formulas for that. All right. So thus we have the following. The total volume, I'm going to take the inner volume V1 and subtract it away from the outer volume V2. All right. Well, the volume for a cylinder is pi r squared times the height. Okay, so pi times the radius squared times the height. Well, if we have volume 2, the outer radius is R2. Volume 1, the inner radius is R1. And you can work through this, right? Like they both have a pi in it, I'll factor that out. They both have an h, I'll factor it out. This is the difference of two squares right here. And then I'm going to do something you're going to see interesting here. I'm going to add a 2 in front here. If I multiply by 2, I have to divide by a 2. All right, why did I do that? Let's see, this R2 plus R1 divided by 2, that's the average of the radius of R2 and R1. Well, if you look back here, I denoted that just as R. All right? So if I let delta R be the thickness, so R2 minus Y1 of the shell, and R equal the average radius, the formula for the volume of our cylindrical shell, all right, that cylinder that I had here, this guy, the volume of this thing, just becomes 2 pi R times the height times delta R. But this is cool, right? Like you can see where this is going. In our previous example, delta R was always like a dy dx in our integral. Our height here, our height of the shell, this height here, is going to be approximated by a vertical rectangle. And then R, the radius, is going to be like some x value here. All right, let me get there. It's pretty cool. All right, so back here we have volume is equal to 2 pi R times the height times delta R. All right, so sorry about that. So we have this. So the equation can be remembered as the following. The circumference, 2 pi R, times the height times the thickness. Circumference times height times thickness. All right. So now let S be the solid obtained by rotating about the y-axis, the region bounded by. So we have this region here, all right. Y is equal to f of x, all right. Y is equal to 0, all right. And x is equal to a and b. So I'm going to take this shape here and I'm going to revolve it around the y-axis here, okay. So you can see what that shape looks like here. Kind of looks like a top with a hole in it. All right, so if we divide our intervals a to b into n subintervals, all right, of equal width, all right. So if you have some interval here and here, all right, the width will be given by x bar sub I, and if we let delta x be the midpoint of the the ith subinterval, that's a little confusing. So let me walk us through it here. All right. So the rectangle with base, the two endpoints x sub I and x sub minus 1. Where its average x values between it, all right, is rotated about the y-axis. So I'm going to take this rectangle here, and I'm going to rotate it around. All right. Well, you could see here how we get the concept of the rectangle. The height of the rectangle here is where it hits the graph, and that's given by x bar sub I. All right. So we've got, think about this, from here to here we have a radius, and then here we have the height. Right? So as a result, the cylindrical shell with average radius x bar sub I and height f of x sub r, f of x bar sub I and thickness delta x, all right? And I'm going to have all these different rectangles. So like this first one here, all right? X bar sub I is right in the middle, and f of x bar sub I is up here. The next one, and so on, and so on, and so on. Well, thus by formula 1, the volume of the ith rectangle is, instead of 2 pi x, it's 2 pi x bar sub I times the height. Well, the height is given by the functional value evaluated at that x value, all right, times the thickness. Well, if I have a bunch of rectangles here, then we can approximate the value by summing them all up. So sum of the volume of the individual rectangles. But then we know from previous classes, right, that like if we want to get the actual area, we will use n rectangles, and we will figure out as n goes to infinity. All right, so approximation appears to become better as n goes to infinity. However, from the definition of the integral, we know that if we take up in some n an infinite number of rectangles, that just becomes the integral from a to b times 2 pi x f of x dx. Like, look at this. The average radius just becomes whatever the x value is. The height is just given by the functional value, and our delta x gets replaced by dx. So this is important here, okay? We are rotating around the y-axis, but it's a dx problem. So like in the previous section, if you were rotating around the y-axis, it would be dy. But here it's dx. All right? So thus the following seems plausible. The volume of solid obtained by rotating about the y-axis, the region under the curve, y is equal to f of x from a to b, is given by that simple integral. All right. So the volume is equal to the integral from a to b out here, 2 pi x times f of x dx. All right, let's go back and look at this problem here that we had. All right, so find the volume of solid obtained by rotating about the y-axis, the region bounded by y is equal to 2x squared minus x cubed, and y is equal to 0. All right, so y is equal to 0 we know is the x-axis. So let's set it up here. All right, so we can see that a typical shell has radius x. All right, each shell has a different x value, obviously. So the circumference is just 2 pi times whatever that x is. And the height here, the height is just given by the functional value. So obviously very easily setting this up. It doesn't get much easier. All right, if you go back here, all right, it's bounded by y is equal to 0. So we see the graph crosses the x-axis here at 0 and 2. So we're going to integrate from 0 to 2. Let me go back, sorry about that. We're going to integrate from 0 to 2, 2 pi x times f of x dx. It's like, that's an incredibly easy integral to do right here. Literally doesn't get much easier than this. So just simply, excuse the typo here, this is supposed to show this as being distributed here. But if you just look at this right here, this immediately will integrate into this. And then plugging it in, you get this. All right, so sorry about that little typo there. But this is what you get. It's not too bad. It's like as soon as you set it up, the integral kind of just like falls into place. All right, so this can be verified by the shell method, which gives the same answer as slicing. All right, and here you can see the computer-generated picture of the solid whose volume is computed in the example. So the thing is if you were to do the shell method, or excuse me, the washer method, you would get the same exact answer. All right. So comparing the solution of example 1 with the marks at the beginning section, we see that the cylindrical shell method is much easier than the washer problem. All right, but here's the thing. In other examples, the washer method might be easier. So this is where it gets a little hard. You don't particularly know which one is going to be easier. All right, let's take a look at another example. All right. So let's find the volume of the solid obtained by rotating about the y-axis. Okay, so we're going about the y-axis with the region between y is equal to x and y is equal to x squared. All right, so now here's the thing. If you're going to use the shell method for this, you got to think about this. Okay, if you're going to use the shell method around the y-axis, this would be a dx problem. If you were to use the washer method, okay, about the y-axis, it would be a dy problem. All right, in your integral. Okay, so if you look here, the region of a typical shell is shown here. All right, so we're going about the y-axis. So the radius emanates from the y-axis. So the radius is just the x value. So the circumference here is 2 pi x. And the height of these shells is just given by the top curve, which is y is equal to x, minus the bottom curve. Okay, so you have to figure out where you're going to integrate from, obviously. So you have to look where does y is equal to x and y is equal to x squared the same? Well, that's x is equal to 0 and 1. So setting up the volume, you're going to integrate from 0 to 1, 2 pi x times the height, which is given by x minus x squared. Well, distributing the x, factoring out the constant, you get 2 pi times the integral from 0 to 1 of this. Well, x squared integrates to this, x cubed integrates to this, and evaluating the integral, you just get pi over 6. So as you can see, just like the previous sections, the actual integral isn't hard. It's setting it up. All right, let's move on. All right. So here's the thing. We've been doing around the y-axis. Let's do it about the x-axis. All right. So as the following example shows, the cell method works just as well if we rotate around the x-axis. Now listen to me. This is important. If you're going to use the shell method around the x-axis, it becomes a dy problem. If you have been doing the washer method around the x-axis, it would be a dx. All right. So let's draw the diagram to identify the height here, and you'll see. Okay, so use cylindrical shells to find the volume of the solid obtained by rotating about, this is important, the x-axis, all right, the region under the curve y is equal to square root of x from 0 to 1. Okay, so to use shells, we labeled the curve. So here's the curve. Y is equal to the square root of x, all right? But since we're going to do shells that are parallel, okay, look at this. It is a horizontal here, and if we go around the x-axis, it's dy. So you need to solve this in terms of y. So to get x by itself, you square both sides, and you get x is equal to y squared. So this top curve here is the same thing as y is equal to the square root of x, or x is equal to y squared. All right, now here's where it gets a little confusing. All right, the height of the curve. If you look up here, the height is 1, but then the height falls, right? So the height falls by whatever y squared is. So our shell height, so listen, this is important, our shell height ends up being 1 minus y squared. Our radius here emanates from here. So from here to here, the radius is whatever the y value is. Okay, so our radius is y. So think about what that means in terms of the circumference. Instead of the circumference being 2 pi x, our circumference becomes 2 pi y. And our height here ends up being 1 minus y squared. So when we plug this in, the volume becomes, we're going from, this is important, from 0 to 1 up here, okay? 0 to 1 along the y-axis. 2 pi times y, so that's the circumference, times the height. Well, distribute the y, you get very simple integral, and this is what you get when you evaluate it. Now here's the thing. This was kind of confusing to set up, like you got the height as 1 minus y squared. In this case, it would have actually been easier to do the disk method, believe it or not. You would get the same result. All right, let's do one more. All right, find the volume of the solid obtained by rotating the region bounded by, this is important here, y is equal to x minus x squared, and I'll show you what that looks like, and y is equal to 0. So where does the graph of y is equal to x minus x squared cross the y equals 0, so that's cross the x-axis. Now this is weird. About the line x is equal to 2. So notice here, okay, that we're not rotating around the x-axis or the y-axis. We're rotating around a vertical line, all right, a vertical line, x is equal to 2. All right, so let's talk about what this looks like visually. So the figures show the region in a cylindrical shell formed by rotating about the line x is equal to 2. All right, so here, right here, here's our graph. So it starts at 0, and as you see here, the graph crosses 1, okay? And we're going to take this and we're going to like rotate it around here. So here's this shell like rotated around, okay? Now here's the weird thing. This graph is going to you're going to take from here and rotate it all the way around. Right? So this thing goes the whole thing around. All right, well, we got our height. Our height is a piece of cake. All right? So if we go around this vertical line, we're going to use parallel. So if you see that this vertical line is like a y-axis here, so since it's vertical, this is going to be a dx, all right, dx integral. Our height from here to here is just given by x minus x squared, but our radius is different. Okay, our radius is actually the hard part. Our radius starts here at 2 and goes all the way out here. So if you think about it, our furthest radius from here to here has a distance of 2. And then our radius falls depending on what the x value is. So our radius decreases by x. So if our radius starts at 2 and then decreases by the x value, our radius ends up being 2 minus x. All right, so think about this. This is where it gets a little tricky when we set this up. All right, we're going to integrate from 1 to 0. All right, I know that seems weird how I set this up. and forgive the typo here, sorry, from 0 to 1. Sorry about the typo. We're going to integrate from 0 to 1. All right. Here, it's 2 pi times the radius. So 2 pi, our radius is 2 minus x, times our height, which is x minus x squared. Sorry about the flip there, the typo. I apologize. And then dx. So factoring out our constant, distributing here, we get the following. And then this is an incredibly easy integral to set up. So I'm sorry about the typo there. Okay, we're going to integrate from 0 to 1. And if you integrate this, you simply get the following. Plugging in 1 and 0, you end up getting pi over 2. All right, everybody. I hope these videos helped. I'm sorry about the 2 typos again here, and then the other one shown above. But as you can see, doing the actual integrals is not hard. Setting them up is. So I encourage you to watch the rest of the videos I posted, and your homework is posted in WebAssign, and good luck.